Hello. So now we are going to discuss light transport from the perspective of diffusion of light. So let's begin. Light transport using diffusion theory. This is a picture of me on the Great Barrier Reef in Australia, where I was studying the light transport in sea coral. Notice how the light spreads by diffusion in the skeleton of the sea coral. This translucent skeleton allows light from the sun impinging on one side to propagate through the skeleton to feed the sea coral living on the back side of the skeleton. It's important that the skeleton is translucent to spread the light out evenly to all of the members of that sea coral community. This is a picture of a leaf illuminated from behind by the sun. Notice how the light has spread out diffusely in the leaf. On the right is a picture of a stretch of the lifetime of a photon, the average length of the lifetime of a photon, 1 over mu sub A. But because of scattering, this photon has spent all its time in this local volume. This is how the leaf uses scattering to confine light, to trap light within the leaf. The vacuoles within a leaf, the little air pockets within a leaf, scatter light so efficiently that the light is trapped in the leaf, which can lift the effluence as much as threefold. That greatly enhances the photosynthetic efficiency. Concentration of light in a cube of water as irradiated by a 1 watt per centimeter squared irradiance can be discussed in terms of the ratio of fluence rate to the speed of light. In other words, the fluence rate is equal to concentration of energy scaled by the speed of light in the medium. If the irradiance is 1 watt per centimeter squared, and you're working with 500 nanometer wavelength light, 1 watt per centimeter squared equaling 0.19 picomolar photons, or pico-Einsteins. So fluence rate and energy density are essentially the same thing. Photons can be discussed as if there is a concentration of energy which can now diffuse in the tissue. Imagine an irradiance on an object, but there are two mirrors that reflect light back onto the object. Then the fluence rate within the object would be 3e, even though only 1e was delivered. In tissue, the scattering properties act like little mirrors. By scattering the light and redirecting it back onto a particular location, that fluence rate at that location increases. This is a 1 millimeter ball of Teflon into which an optical fiber has been inserted. If you place this in water and irradiate it with a known irradiance, the photons will strike the ball and diffuse into the center and then be collected by the fiber and routed to a detector. This can be used to calibrate the probe. Now the probe can be put into some unknown tissue or turbid light scattering medium where light will be impinging from all directions onto this probe. However, the photons will still diffuse into the center and be collected for detection. Hence, this probe becomes an isotropic probe. We can place an isotropic probe in a fish tank filled with milk with some ink in it to make it a light gray, and move that detector back and forth as we irradiate with a collimated laser beam. If you only have clear water in the fish tank, you just register 1 unit of fluence. But when you added the milk and ink, you built up a concentration almost threefold in the fish tank. The scattering has caused a concentration of photons near the surface. If you fill this outer compartment with water, no longer will there be an air-water interface, and total internal reflectance will no longer occur. Photons will easily escape out, and hence there's a slight drop in the fluence. Therefore, boundary conditions do matter. When we deliver light by a narrow beam or by an optical fiber, the light is thrown forward one transport mean-free path, and then light diffuses down concentration gradients. We could use classic diffusion theory to discuss the diffusion of light. In classic diffusion theory, Fick's law says that the flux down a concentration gradient is related to minus the diffusivity times the gradient. The gradient is negative because it's dropping, but minus that is a positive, times chi gives you a positive flux down the gradient. If you have a source near a position, a layer, the flux at the front of that layer is steeper than the flux at the end, the rear of the layer. Hence, you are filling that layer faster than you're depleting it. So the concentration increases as a function of time. And Fick's second law says the change in concentration with respect to time is chi times the second derivative, the curvature of the concentration. If you have a sink near that layer, then the depletion of light from that layer is faster than the input of light, and therefore the concentration decreases with time. So the sinks and the sink and the source cause problems for diffusion theory. But in the region where the gradients are rather shallow, then diffusion theory works very well. So classic diffusion theory, for the diffusion of any material or unit of energy, such as heat or sugar molecules, U0, is a concentration as a function of time at some position r distant, and a distance r from the source. It's equal to this expression, which is an exponent, a Gaussian exponential, with a denominator that has the diffusivity and time. The factor m changes whether you have 1 for planar, 2 for cylindrical, or 3 for spherical diffusion. We're going to use m equals 3. So this diffusivity is now chi squared, centimeters squared per second, times time, which is centimeters squared. 1/2 is the square root, and m equals 3 raises it to the third power, so it's now centimeter cubed. So it's the number per centimeter cubed. How do we apply this to optical diffusion, the diffusion of photons? We simply replace chi by cd, where c is the speed of light in the medium, and d is the diffusion length, 1/3 of 1 over mu sub a plus mu sub s prime. Units of centimeters, speed is centimeter per second, therefore this CD product is centimeters squared per second. That gets substituted in the expression. And now, this describes the spreading of light by diffusion. We add a term to account for the absorption of light, e to the minus mu sub a ct. Ct is a path length, so this is simply a Beer's law expression. This term controls the spreading of light. This term controls the attenuation of light, the extinguishment of light. Now this is energy concentration, joules per centimeter cubed, but we know that we can multiply by the speed of light and get the fluence rate, watts per centimeter squared. So now we have the full expression for time-resolved light transport by diffusion in a tissue. Let's take this entire function and place it in an integration over time, integrating from 0 to infinity. Therefore, we only have a function of r, which is the radiant exposure, joules per centimeter squared, that have occurred at a given position. Doing this integration yields u naught e to the minus this term over 4 pi dr. This term is actually equivalent to delta, the 1 over e penetration depth. And therefore, this can be restated as simply e to the minus r over delta over 4 pi dr. This is a very useful expression. It is a point spread function for the radiant exposure from a point source in 3 dimensions. Let's look at that more closely. As a function of time, if we had an impulse at r equals 0, then at r equal 1 millimeter, we can chart the time course of fluence. It rises from 0 up to a peak very quickly. It's only 1 millimeter away. And then it drops very quickly because the light is spreading rapidly. And the area under the curve is 14.8 joules per centimeter squared. Over here, we're at 5 millimeter distance, and it takes about 50 picoseconds for the light to reach a peak at that position. The value of the light, this axis is 100 times less than this, so this is much lower. The area under this curve, going all the way out to infinity, is 0.29 joules per centimeter squared, about 50-fold less. The point here is that the fluence rate is the curve versus time, but the radiant exposure is the area under the curve. So if we had an impulse, this would be the response at a function as a function of position r. But what if we had a series of impulses? Then we would add up the contribution to h of r after each impulse. If the frequency of impulses was some frequency f, but the average power was p naught in watts, then the energy per impulse would be p naught over f. In order to keep the average power constant, u naught would decrease as frequency increased. In the limit of frequency going to infinity, this equation transforms into the expression for power. The power, the fluence as a function of r is p naught e to the minus r over delta over 4 pi dr. This should be a phi, not a p. Sorry. This is a most useful expression. You might want to pause and just write this down if you're not already familiar with it. So we can convolve that point spread function over a set of sources distributed in a light scattering medium. Each light source has a point spread function, but the radiant exposure or the fluence rate from all of those points superimposes, and so we build up the pattern of fluence from all 40 sources. This is very flexible, and you could approach many different problems by such superposition. Now let's look more closely at how phi decays as a function of distance r. If you keep the scattering constant, but increase the absorption, with no absorption, the light falls off as simply 1 over r. But as you add absorption, it falls off much more quickly. So this fall off has very little influence from absorption near the source. It really doesn't matter how absorption increases. The fall off near the source is the same. The scattering is important near the source, but the absorption doesn't have enough path length yet to assert an effect. Only when it's distant and at large r is there enough diffuse light propagation that the path length can scale the absorption coefficient and cause attenuation. If you keep absorption the same and only change the scattering, then the effect is actually felt everywhere. Scattering affects the fluence rate near the surface. Again, this should be a phi. Fluence rate is power times this expression. If we look at the total diffuse reflectance versus the ratio of reduced scattering to absorption, we see a very simple pattern. There is a sigmoid shape on this semi-log plot. RD has a simple expression, e to the minus 7 over the square root of 3 times 1 plus n prime being this ratio of reduced scattering to absorption. As scattering increases relative to absorption, you get more reflectance. And as scattering decreases, reflectance drops. So let's consider a cup of coffee with cream. And let's shine light on it and measure the reflectance coming off the coffee. Or let's look at it with your eye, and your eye is seeing the color of the coffee, and that's the eye's way of making a measurement of reflectance. Now let's add some water to the coffee. What happens to the reflectance? Does the reflectance increase, decrease, or remain the same? What do you think? You're diluting the coffee. Is it going to increase, decrease, or remain the same? Well, consider the photon entering the tissue and scattering its way till it reflects. The reflectance is e to the minus mu sub a times some total path length L, which is equal to 1 over mu sub s prime, the step size, times the number of steps. Therefore, it's equal to e to the minus n mu sub a over mu sub s prime. Now let's add the water. And notice what happened to the path length. It got bigger because the step size got larger. We diluted the scattering, so the step size is now bigger. We have a larger path length, but we've also diluted the absorption. And since the absorption and scattering are both diluted the same, it cancels, and we get exactly the same expression. Therefore, the reflectance does not change. Now, I use this every day. This is very useful. When I buy a cup of coffee, it's black. But I don't know whether I've got good coffee or bad coffee. Do I have strong coffee or weak coffee? The reflectance is related to the ratio of mu sub s prime over mu sub a. Initially, mu sub s prime is almost 0, so reflectance is 0 and it looks black. Now I add some milk, a tablespoon of milk or a little tub of milk, but a standard amount of milk. Therefore, I've increased mu sub s prime by a known amount. Now the reflectance may be very high after adding milk because the absorption was actually quite low. So a known amount of scattering over a very low absorption suddenly gives you high reflectance. The coffee now looks rather white, so it's a weak coffee. But if the coffee was strong coffee, the denominator would be a very high absorption. Adding a known scattering increase still leaves the reflectance rather low due to this high absorbing denominator. The coffee looks dark brown and rich, and I have good coffee. So here's the coffee after adding the milk, and it looks brown. If you wish to read more about diffuse light transport, this tutorial, written with Brian Pogue, may be of interest to you. So, the key lesson I've tried to get across in this discussion is that fluence rate is actually the same as concentration of energy due to photons. And since concentration is the key aspect of diffusion down concentration gradients, it makes total sense to discuss the diffusion of photons down concentration gradients using standard diffusion theory. All you have to do is replace diffusivity with CD, speed of light in the medium, times the diffusion length. And you can add an attenuation, Beer's law attenuation, e to the minus mu sub a CT. That's the concentration. Multiply times the speed of light in the medium. And now you have the fluence rate. You have the time-resolved fluence rate. Integrated over time, you get the radiant exposure. Convolve that impulse response of radiant exposure over a set of impulses in the limit of very high frequency of impulses, and you now have the fluence rate equal to power times a very simple expression. This expression can now be convolved against any arbitrary source distribution. And this is a very powerful yet simple technique to make estimates of how light diffuses into and through tissues.